Okay, so what are you seeing now?
We see the sporadic groups. It's like a blank slide. Yeah.
Okay, so the entire screen is a sporadic group slide with a possibly a small picture of me in the corner or something.
Uh, yeah, kind of, yeah.
Okay, well, it looks like everything is working as far as I can figure out. So what time does it start? 2 o'clock?
Yeah, it starts at two.
Okay, well, this always happens whenever you check everything early, everything works. It's only if you check things at the last possible minute that they go wrong.
Yeah. Wait, we see like the whole slideshow. I don't know if you're
On,
if that
on,
was
on the left,
yeah.
I mean, well, that's harmless. I mean,
Okay.
think I can eliminate it if you think that looks better.
Or whatever works for you.
Yeah. I haven't managed to figure out how to eliminate all this junk on the right. I don't suppose anyone knows how to do that.
Uh, there's a play button on the top. I don't know, maybe that would.
I tried pressing that when experimenting. It just seemed to make things get complicated. So
Okay.
I'm I'm rather wary of experimenting because it can cause things to go wrong in an unrecoverable way.
Yeah, okay.
So unless someone happens to know how to get rid of it, I think we'll just leave it. So that's okay, so that's just see what this does. I wonder what this one does. That I could try play and see what happens. Okay, what does that look like now?
Now we don't have the right side or anything. It's just your slides. Yeah, it looks better, yeah.
Only thing is, I can't figure out how to get the next slide. Oh yes, that seems to work. Uh,
Awesome. Yeah.
so do you see anything other than a blank slide? I mean, is there a sort of little picture of me or something?
No, we just see when you're sharing, we just see the blank slide, but we can see you like through the Zoom.
Okay, so you see the blank slide and me in.
Yeah, yeah.
Okay, maybe this is the best arrangement then. No, lost my mouse weapons of. Oh, okay, so that leaves it and that starts it off again. Okay. Okay, so I think I'll wander off and be back in 7 minutes or so.
I think like a few more minutes and then we can start. Like a few people are running late. Maybe like 2 or 3 minutes if that's fine with you.
Sounds good.
Um, Okay, guys, I think we can start now. So, hello, we are CMC. So, welcome everyone. We are really honored to be joined by Professor Borcherds today for our session on sporadic groups. Professor Borcherds is a professor of mathematics at UC Berkeley. In 1998, he was awarded the Fields Medal, which is widely considered the highest scientific award in mathematics. He received this award for his revolutionary work in algebra and geometry, most notably for providing the famous Montrose-Moonshine conjecture. We are absolutely thrilled that he is here to share his time and expertise with us. So please welcome me with Professor Borcherds.
Okay, thanks. I'd just spend a few seconds just checking everything is working okay. So you should all be seeing a blank slide with the word sporadic groups at the top, and you should be able to hear me. Is is this what everyone is seeing? Well, I've no.
Yeah,
Okay.
yeah.
Okay. So this talk would be about sporadic groups. So what I'm going to do is I'm going to start explaining what a group is and then explain what makes it sporadic. Oh, hang on. Something has gone wrong with already. Okay, unfortunately, things seem to have jammed and I can't go to the next slide, and I can't figure out why I can't go to the next slide. Okay, we tested this 2 minutes, about 5 minutes ago, and it was all working fine. Now, whenever I click on the thing to the next slide, it just beeps at me.
Maybe try like leave exiting and then like opening it, like press escape maybe.
Escape, it just makes another small beeping noise.
Oh, okay, wait, click your screen. You might be like still on like the Zoom. Okay.
Okay, it seems to be working now. I don't know what was causing that problem. Okay, so here are some pictures of symmetric and possibly non-symmetric objects. So most of these objects are kind of very symmetric, which means if you sort of pick them up and put them back down in a different position, they look the same. On the left, two non-symmetric objects, which are a potato and a fiddler crab. And you can see that the non-symmetric objects kind of look a bit ugly. Can we turn off the regular beeping from people arriving? This is getting a bit distracting.
Yeah, I'll turn it off.
Yeah. So humans kind of like looking at things that are symmetric, and apparently this is something to do with the fact that being symmetric is a sign that there's nothing wrong with you. Like if you have some disease, it's probably going to affect one side of you more than the other, so you'll look unsymmetric. So humans don't really like looking at things that aren't symmetric. And group theory is essentially the study of symmetry. What is a group? Well, a group is just the collection of symmetries of something. So if we take an object like a tetrahedron, which has 4 triangular faces, you can see it's got 12 symmetries because you can pick one of its 4 faces and then you can rotate by 3 things on each face. Altogether, there are 12 ways to pick up a tetrahedron and put it back in the same place. And similarly, a cube has 24 symmetries. If you've got a Rubik's cube, this is a very large number of symmetries because there are all sorts of ways you can twiddle it and still have it looking like a cube. And the basic invariant of a group is just the number of its elements, which is called its order. So the symmetry group of a cube has order 24, and so on. And what we want to do is to classify all possible groups, and we classify them in terms of their order. For instance, there are 2 different groups of order 4. So on the top half of this slide, I have a lot of objects, and the symmetry groups of these are all really the same. I mean, the objects look different, but if you look at the symmetry groups, it's sort of essentially the same in some sense. And there's one symmetry of order 1 where you just do nothing, and 3 symmetries of order 2. And when you say symmetry is of order 2, it means if you repeat that symmetry twice, you get back to where you started. On the bottom of this slide are some objects with a symmetry group, another symmetry group of order 4. And this group is different from the ones in the top because on the bottom there are some elements of order 4. For instance, if you take this funny knot on the left at the bottom and rotate it by 1/4 of a revolution, you can repeat that 4 times to get back to where you started. So there's a symmetry of order 4, whereas the objects in the top don't have a symmetry of order 4. So for a given order, there can be more than one sort of group with that order of symmetry, with that number of symmetries. So here's a problem for you. Suppose I take a tennis ball, and if you sort of stare at it thoughtfully, you'll see that it's actually got 4 symmetries because you can pick it up and put it back in the same place in 4 different ways. I mean, there are infinitely many if you think of it as a sphere, but you notice it's got this sort of funny wiggly line on it, and this means that it's only got 4 symmetries. So there's a problem. Which symmetry group does it have? Is it the one with 3 elements of order 2, or the one with an element of order 4? And I must admit, I can never remember the answer, and I get confused when I try and figure it out. Okay, so how about an apple? How many symmetries does an apple have? Well, you might think it's got infinitely many because you can just rotate it. But if you cut an apple in half, you will find that seeds are arranged in this nice pentagonal pattern. So if you count rotations and reflections, it actually has 10 symmetries because you can rotate it 5 ways, and then you can also reflect it in 5 different ways. So altogether, it's got 10 symmetries, and if you count them up, there are 5 of order 2 and 4 of order 5 and 1 of order 1. So that's a typical example of a slightly more complicated group. And we can ask how many groups are there of various small orders, and you can go through the orders up to 10, and you find there are 2 groups of order 4 and 2 of order 6 and 5 of order 8. Here are a few objects on the right with some of these symmetries. For instance, if you take a regular pentagon, it's got 5 symmetries if you count rotations, and 10 symmetries if you count rotations and reflections. Wait a moment. Oh, this is now working. Okay, and we can ask how many groups are there of larger order. So if you go up to order 64, there are 267 groups. And if you go up to order 1024, then there are some ridiculously large number of groups. Obviously, you need to use a computer to count these. It's too many to do by hand. However, the order of a group doesn't, the number of groups of a different order doesn't depend just on the order. For instance, if you ask for groups of order 1,000,003, there's only 1 group of that order. And the reason is that 1,000,003 is prime. And it turns out that the number of groups of a different order depends more on the number of primes dividing the order than on the order itself. So for instance, 1024, there are 10 primes dividing the order, and that means there are a huge number of groups of that order, whereas 1,000,003, there's only 1 prime, so there's only 1 group. So we find it's classifying all groups of order n is just hopelessly complicated if n is large. I have a picture here of one of the groups of order 64, so you can sort of see how complicated it is. So what this is a picture of is a picture of, you take a group of order 64, and there are lots of smaller groups inside it. So it turns out that it's got groups of order 2 or 4 or 8 or 16 inside. And this is a sort of picture of all the groups living inside one particular group of order 64. So as you can see, they look pretty complicated inside. Okay, so how can you classify all groups if there are too many to classify? Well, this problem was first studied by Galois. Here's a sort of picture of him, and he's most famous for he managed to get himself killed in a duel at the age of 21. So it's kind of a bit depressing, because you think, at the age of 21, I was sort of doing exams as an undergraduate, and meanwhile Galois had done something that has made him world famous for as long as civilization lasts. So anyway, what he suggested was just classify simple groups. So let's look at an analogy. If you're a chemist, you can't possibly classify all chemical compounds. For instance, here's a picture of DNA on the left, and you can see it's ridiculously complicated, and you can't possibly write down all compounds. However, what you can do is you can notice that all chemical compounds are built out of atoms, and we can classify the atoms. There's about 100 of them, and you can put them into this nice table. And then we've got a sort of classification of molecules, because they're all built out of atoms, and the atoms are joined together by bonds, and there are lots of ways of joining atoms together, but in some sense, we sort of have a rough classification of all compounds. And we can do the same with groups. We can split all the groups into groups that can't be split up any further. And these aren't called atoms, they're called simple groups. This is really bad terminology, because the simple groups are not simple at all, but whatever, we're stuck with it. So here is a sort of picture of all simple groups. Some guy arranged them in a table that looks like the periodic table of elements just for fun. There's no particularly good reason for doing this. It's just the idea is that what we do is we get that there are actually 18 infinite families of simple groups, and there's 26 of them left over. The 26 leftover ones are called the sporadic groups. So what do the simple groups look like? Well, here's some pictures illustrating the easiest non-cyclic simple group. This is the icosahedral group, which has 60 symmetries. And what I've done here is I've collected a collection of common objects, all of which have the icosahedral group as their symmetry group. So all of these objects have about 60 symmetries. Well, it depends. Well, that's not quite true. Most of them actually have 120 symmetries if you allow reflections, but if you only allow rotations, these all have exactly 60 symmetries. In the top in the middle, there's a picture of a virus, and then there's an icosahedron and a dodecahedron and a few other common objects. So there are actually quite a few viruses which have icosahedral symmetry. So here's an actual photograph of an adenovirus. On the left is an electron micrograph of it, and it's a bit hard to see that it's an icosahedron. So on the right, I've put white spots at all the 12 vertices, and you can see, if you look carefully, you can just about see some equilateral triangular faces. The picture in the middle gives a sort of diagram which makes it a little bit easier to see the symmetry. You can see it's built out of lots of things, that proteins that are almost spheres that cleverly fit together in this way. And another of the fun things that have this symmetry, that there are some small microscopic animals called radiolarians, which look really cool. So here are some pictures of them drawn by Ernest Haeckel. He's got this rather nice book which contains pages and pages of these extraordinary drawings of microscopic animals. So the one on the top left is the one with icosahedral symmetry. And you can ask, how do you know these are all the finite simple groups? Well, we have a proof that these are all the finite simple groups, which is the longest proof that has ever been written by humans. It's about 10 or 20,000 pages long. And this pile of books here is a collection of books about the proof, which cover most of it, not quite all of it, but it gives you some idea of how complicated this proof is. You know, it's a stack of books about 1 meter high, and you know, there are maybe half a dozen people in the world who have a reasonable idea of what's actually in this proof. There are far longer proofs that have been produced by computer, but this is the longest human written proof that has ever been produced. So what do these infinite families look like? Well, the simplest ones are just cyclic groups. These are where you take a regular polygon with a prime number of sides and just look at its rotations. So these are the easiest sorts of groups to think about. And then you get things like alternating groups and general linear groups. And general linear groups just look like groups of matrices. They're actually not quite simple. You have to twiddle them slightly to make them into simple groups, but roughly speaking, they're simple groups. And there are other infinite families called orthogonal and unitary and symplectic groups and so on. So how does the classification work? Well, I said it's 10,000 pages long. Obviously, I'm not going to be able to explain it in any serious way. The basic idea was started by Brouwer, who said what we should do with a simple group is look at an involution, which has an element of order 2, and then look at all the ways this element of order 2 can be embedded in the group. And it takes 10,000 pages to make sense of that. Some of the examples of sporadic ones were discovered by this guy called Mathieu in 1861, which was really amazing because groups had only just been defined about that time, and he managed to find these bizarre groups. So he found these 5 mature groups, which have been puzzling people ever since. The smallest one has order 7,920. And there's no real easy way to say what these groups are. I mean, John Conway had this way of taking one of these mature groups as a sort of sliding block puzzle on a graph on 13 lines and 13 points, but it's not something you would think of very easily. Next, I want to talk about something that is apparently completely different, which is how do you pack spheres? So let's first of all look at how do you pack spheres in 2 dimensions? Well, everybody knows how to do that. You can pack them on a square grid as on the left, and that gives a reasonably dense way of packing spheres. And then you can pack them more tightly by putting them into this sort of hexagonal lattice. So you see that there's a sort of hexagonal or possibly triangular lattice where you can pack them more closely. And you can ask the same question in 3 dimensions. So how do you pack spheres in 3 dimensions? And this was actually a problem that was studied a few hundred years ago by the Navy, because the Navy wanted to take lots of cannonballs on its ships, and they actually wanted to know how many you want to pack as many cannonballs into as little space as possible, because the old sailing ships were really, really short of space. So here's an example of how to pack cannonballs. And there are actually many ways of packing cannonballs. You can start with packing cannonballs in a nice hexagonal packing in the first layer in white, and then you can put a second layer on top of that in black by putting cannonballs in the holes or gaps in the first layer. And then you can put a third layer on where you put the cannonballs in gaps in the second layer. But it turns out there are 2 ways of doing this. So you can either put the third layer directly above the balls in the first layer, or you can put them so that they're sort of above gaps in the first layer. And this actually gives infinitely many ways of packing cannonballs in 3 dimensions, because each layer you add, you have a choice of 2 ways to add the layer. And there are, in fact, 2 common ways of doing this in 3 dimensions, which are called face-centered cubic and hexagonal close packing in 3 dimensions. Next, you can ask how many ways are there in higher dimensions? Why? Well, because we're mathematicians and like looking at pointless problems in high dimensions. In 4 to 7 dimensions, we've got some pretty good guesses for what the answer is, but we haven't managed to prove it. in 8 dimensions, we know the best packing. It's called something called the E8 lattice that I'll say a bit more later. In 9 to 23 dimensions, again, we're not quite certain what the best packing is. In 24 dimensions, we know the best packing. And this is really, really bizarre. We can do 8 and 24 dimensions, but we can't do the dimensions less than that. So the proofs in 3 and 8 dimensions, well, the 3-dimensional proof was done a few years ago by Thomas Hales. And his proof is billions of lines long. It requires computer calculations that have to consider billions of different cases. So this is an example of a proof that is far longer than the classification of sporadic groups, but it's not a human-generated proof. It was generated by a computer. The proofs in 8 and 24 dimensions were found by Marina Wiazowska about 10 years ago. And she has this really, really bizarre argument that only works in these dimensions, and people have tried very hard to make it work in other dimensions, but it just doesn't seem to work. There's something very peculiar going on in these 2 dimensions. So I'll try and explain how to describe these sphere packings. What you can do is you can just give the coordinates of the centers of the spheres. So I'm going to take a break for a minute or two because my voice is getting a bit hoarse, and maybe if I drink a bit of water. Okay, seems better. So for a cubic packing, the centers of the spheres will just be all points whose coordinates are 3 integers. So you can see there are 6 spheres touching the sphere at the origin, so each sphere touches 6 others. For the face-centered cubic, you have to do something a little bit trickier. You take all the points with integer coordinates such that the sum of the coordinates is even. And then you can see there are 12 spheres touching the sphere at the origin. Now we can describe the E8 packing. It's kind of similar, except you take all points and the coordinates have to be all integers, or they're all integers plus a half, and the sum has to be even. And if you count very carefully, you find there are 240 spheres touching a given sphere. It's a bit difficult to draw pictures of this packing in 8 dimensions because we only have 3 dimensions to draw it. You can try and draw the 240 spheres touching a given sphere, and if you project this down into a plane, you get this rather complicated pattern looking like this. So there are sort of 240 points in this graph, and there's a line between 2 spheres if they touch or possibly don't touch. I can't quite remember. So you can see this is quite a complicated configuration. And one way you can get simple groups is by looking at reflection groups. These are groups generated by reflections. So here I've got, it starts off here, there are 3, the first 3 are 3 planar reflection groups. You can see that these 3 patterns with triangles, squares, and funny non-equilateral triangles have a lot of lines where you can reflect the group, and all these reflections generate a big group of symmetries. At the bottom, we've got 3 spherical reflection groups where you can reflect the sphere in various great circles. And the remaining 2 patterns are called hyperbolic reflection groups, which look a bit funnier. All these curved lines you see on the hyperbolic, on the 2 remaining ones, are really straight lines in hyperbolic space, and they look curved because hyperbolic space gets bent a bit when you fit it into Euclidean space. And the E8 lattice has a rather big reflection group. So if you look at the symmetries of a group of a cube in 3 dimensions, it's got 9 reflections, which correspond to reflections orthogonal to the following 18 vectors on the top of the slide. You can do the same thing in 8 dimensions. If you write down the 240 vectors that I had earlier, you can reflect in the hyperplanes orthogonal to that, and that gives you 120 reflections. And these generate a group of symmetries of the sphere packing in 8 dimensions. Now we get onto Conway's group. I'll start with a picture of John Conway. He had many mathematical accomplishments, but I think the accomplishment that he used to boast about most often was the fact that he could make his tongue form more patterns than anybody else in the world. He said there were sort of 20 different funny patterns people could make their tongues into, and he had calculated he was the only person who could do all of them. So here he is demonstrating one of them. John Conway discovered an amazing new simple group that was really a symmetry of a sphere packing in 24 dimensions. So here we have a few symmetry groups in 2 dimensions. We've got a symmetry group which has 12 elements. You can see it on the top right. In 3 dimensions, if you take the sphere packing in 3 dimensions and look at its symmetries, you find there are 48 symmetries fixing a sphere. For the 8-dimensional packing that I mentioned earlier, you find it's got about 700 million. And Conway looked at a sphere packing in 24 dimensions and found it had this ridiculously large number of elements. So this gives you a group of symmetries called the Conway group. And it's very nearly a new sporadic simple group. I think it's off by a factor of 2. And Conway discovered this in about 1967 and became world famous for finding this new group, and was invited all over the world to give lectures on it and so on. And I can describe Conway's group as follows. So suppose we look at this pile of cannonballs we had earlier and ask how many cannonballs are there in this pile? Well, there's 1 squared cannonball in the first row, and 2 squared in the second row, and 3 squared in the third row, and so on. So the total number is 1 squared plus 2 squared plus 3 squared up to n squared. And now you can ask, when is the number of cannonballs a square number? And apart from the trivial case when there's only 1 cannonball or 0 cannonballs, there's only one solution, and that's when you have 24 rows, and the sum of the squares from 1 to 24 is 70 squared. Now we can use this to construct Conway's group. So what we do is we work in 26-dimensional space. And we're going to work in 26-dimensional Lorentzian space, which is what people use in special relativity. And this is where we define the distance in a funny way. So if you look in the second row, we normally define the distance as the square root of a squared plus b squared plus c squared and so on. But if you look carefully, I've put a minus sign in front of the a squared. So, as I said, in special relativity, this is exactly how you define distances. And now I'm going to define this vector w, which is going to be 70, 0, 1, 2 up to 24. And now w has length 0. So if you're doing special relativity, you would say that w is the sort of vector on the light cone. And now using this vector w, we can construct a packing in 24 dimensions called the Leech lattice, which is more or less formed as follows. You take all the coordinates to be integers or half integers, just as we did for E8. The sum of the coordinates is even. And finally, the vector must be orthogonal to this funny vector w. And this construction only works in 24 dimensions because we need the vector W, for various reasons, must have length 0. And we can only get a length 0 vector like this in 24 dimensions. So this gives a one-page construction for each lattice. And Conway's group can now be defined as all the symmetry groups of that lattice. So here is a one-page construction of Conway's simple group. Next, we move on to moonshine, and we will start with John Mackay's T-shirt. So John Mackay discovered this amazing fact that 196883 plus 1 is 196884, and he had a T-shirt made with this that he was so pleased about it. And now I want to explain why he was so excited about this. The reason is that 196883 is the dimension of a space in which a sporadic group called the monster lives. And 196884 is the dimension of, is a coefficient of something called the elliptic modular function. So I'll now try and explain what both of these are. There's a bit of a problem here because it's, you know, these two numbers are very close, but this might be a coincidence. I mean, mathematics, you get lots of weird coincidences because we have a lot of small numbers and many of them are close to each other just by coincidence. So here's an XKCD cartoon about e to the pi is very close to pi plus 20, but that's a meaningless coincidence as far as we know. And Ramanujan had a notebook where he found various other funny coincidences. So if you look at e to the pi times the square root of number, it's very often, very roughly, very, very close to an integer. For instance, e to the pi root 163 is this number here with 12 nines. And how do we know this is meaningful and not just a coincidence? For instance, if you look at the bottom, we've got e to the pi times the square root of 1. And that's, you know, it's about 20 plus pi, but that is probably just a meaningless coincidence. Next we need to look at Klein's modular function. So Klein was this German mathematician, and there was a strict rule in the 19th century that all German mathematicians had to have formidable German mathematical beards. So here's Klein with his mathematical beard, and on the right is what he's most famous for, which is called a Klein surface. Well, except it was the German for a surface is Fläche, and this got mistranslated into English as flask, which means bottle. So his surface ended up being called a Klein bottle. And now in German, it's again called a Klein bottle because they took the English word bottle and translated it back into German. So the name's got a bit muddled up. And Klein, as well as inventing his bottle, invented this modular function, which there's actually a slight misprint in it here. But I don't suppose you really care about that. And this can be written as a power series in this number q. And if you look at this power series, you see one of the coefficients is this number 196884. If you want to see a picture of this function, there's a very nice book by Janke and Emder, who drew pictures of Klein's elliptic modular function. You can see it's this really complicated function with all sorts of poles all over the place. What is really impressive is they drew these pictures long before computers were available. So these pictures were actually drawn by hand. I mean, it must have taken many, many hours. And now we can explain why e to the pi root 163 is almost an integer. Well, it turns out that if q is e to the minus pi root 163, then this number 1 over q is very close to e to the pi times root 163. On the other hand, for this number of q, Klein's modular function j of q happens to be an integer for rather subtle reasons coming from complex multiplication. The integer is actually this number minus 26253741268076800. Now this number 1968884q looks large, but it is in fact tiny because the number q is ridiculously small. It's e to the minus something large. So this explains why e to the pi root 163 is very close to an integer. Excuse me while I just get another drink. So that's explained the number 1968884. Now I want to explain the number 1968883. So as we saw, we saw the icosahedral simple group lives in 3 dimensions and has 60 symmetries. Conway's group, I said, lived in 24 dimensions and has this ridiculously large number of symmetries. And Fisher and Grice discovered an even bigger group by starting with the Leech lattice and then, in some sense, working up from there. And they found this ridiculously large group called the monster living in 1968883 dimensions. So where does this dimension come from? Well, if you look at the Leech lattice, each sphere touches 196560 other spheres, and this number is actually close to 196883, and that's not a coincidence. There's a way to build the monster group starting from the Leech lattice, which was found by Robert Grice. And it has this utterly absurd number of elements. So it's the largest sporadic group. Here's a picture of something called the monster character table. This is actually only a very tiny piece, and it's out of focus anyway. I don't know whether you can read it, but if you look at one of the entries, is 196883. And that says the monster can be found in 196883 dimensions. And the next entry is 21296 something 576. And that says the monster can also be found in that number of dimensions. So that there are various dimensions where you can find the monster group. And John Mackay pointed out that this number of dimensions, 196883, that the monster group lives in, is very close to one of the coefficients of the elliptic modular function. And your reaction to this is obviously just a coincidence. If you write down hundreds of numbers, some of them are going to be roughly the same just by chance. But then they found the next coefficient of the elliptic modular function is the sum of the first 3 dimensions that the monster lives in. And it turns out that all coefficients of the elliptic modular function are closely related to dimensions that the monster lives in. And this is obviously now more than a coincidence. And this was sort of explained by Frenkel, Lepowski, and Merman. What they discovered, they discovered something called an infinite dimensional graded vector space. And on the one hand, the monster acts as symmetries of this. And on the other hand, the coefficients of the elliptic modular function appear in the structure of this space. The construction of this is rather complicated. It turns out to be related to string theory. So string theory, as you've heard, is this supposed theory of everything. And it's a bit difficult to get it lined up with the real physical world. For instance, the early versions of string theory only worked if space-time was 26-dimensional, which was a serious problem for physics because space-time is not 26-dimensional. But it turns out to be really great for mathematicians because I mentioned earlier that we construct the Leech lattice by starting in 26 dimensions and then working down 2 dimensions. And it turns out this is exactly the same 26 that turns up in string theory in some sense, that the string theory living in 26 dimensions means that it works really well in relation to the Leech lattice and is also used in constructing this monster vertex algebra. And so that the monster group is related to the elliptic modular function. It turns out that many other sporadic groups are also related to other modular functions. For instance, there's another group called the baby monster, whose order is ridiculously large, but nowhere near as large as the monster group. And it has representations of dimension 1 and 4371 and so on. And there's another more complicated function whose coefficients are very similar. So the function has a coefficient 4372, which is very close to 4371. And there are some more problems like this that we don't yet really understand. So here are some open problems. Ramanujan was this famous Indian mathematician who wrote down thousands of these utterly bizarre identities. A century later, people are still trying to figure out how he found these identities. Ramanujan actually explained how he found them. He said he went to sleep and in his dreams, an Indian goddess showed him these identities, which doesn't really help everybody else in understanding them. And one of the identities he discovered involved things called mock theta functions. One of his mock theta functions looks like this. And people noticed that the mature sporadic group of order about 250 million, it lives in various dimensions. People noticed that these dimensions also appeared as coefficients of this mock theta function. And people have been looking at this, and there's a lot of numerical evidence that these things are connected. But as far as I know, no one's yet come up with any really convincing explanation for why these things are related. So this seems to be an open problem to understand why the mature group should be related to mock theta functions. And this, the existence of sporadic groups is a real philosophical puzzle. If you look at the axioms for a group, they're one line long. I've written them down here. And they look really, really simple. They're simple and natural. And somehow, if you write down these three trivial axioms, the monster group, which is a mind-bogglingly complicated object, is somehow hiding in these trivial axioms, but it takes 10,000 pages to extract it from these axioms. So we have this open philosophical problem. Is there some uniform explanation of why these sporadic groups exist that takes less than 10,000 pages? No one's managed to think of anything better. Okay, so I was going to finish about a few minutes early just to leave time for questions. So I'll finish with this final slide, which gives a few places where you can read about what I've been talking about. So there's a popular book, something of intermediate level. And if you really want to get into this, there are a couple of really advanced mathematical books at the end. Okay, that's the end of the talk. If there are any questions, feel free to ask them.
Thank you for giving the talk. A few people had some questions. So the first one was, does order vary by dimension and rules of symmetries? If so, what are the patterns?
The answer is yes. The order does depend very much on the dimension. And the other answer is that patterns are really complicated and mathematicians have been studying them for a century. I think at one of the earlier slides, we had the monster character table, and this show. So the top left, this ridiculously large number is the order of the monster. The third row gives the order of some of the dimensions that the monster lives in. This only shows the first 10 rows. There are actually about 200 rows because there are 200 dimensions the monster lives in. So one answer to your question is if the order is this monster order, then the corresponding dimensions are given by these 200 numbers. As you can see, there are no particularly obvious patterns in this. There are some very subtle patterns, but as I said, plenty of mathematicians have spent their entire lives studying these patterns.
Okay, thank you. Another question that we had is for the Leech lattice, there was like a minus a squared. And
Yeah.
is the a arbitrary, or is there some way to like set what the a was?
Oh, let me just go back to this slide. Okay, so we had this distance a, b up to z. Here the a is, to start off with, we can think of a, b, c, d, and so on as just being real numbers. So these are coordinates for 26-dimensional space. And we're putting a funny distance on it. So it's space-time, not Euclidean space. And then we're going to restrict all these numbers a and so on. So the restrictions are given below. So in fact, we're going to insist that all these numbers a, b, and so on are actually all integers or integers plus a half. So these numbers, the number a ends up being either an integer or an integer plus a half.
Somebody was wondering why are they called monsters? Like, where did the name come from?
Well, the name was actually introduced by John Conway, and it wasn't actually all that popular. I mean, I think normally groups are named after the people who discovered them. So the standard name for the group would have been Fisher-Grice group, because Fisher and Grice were the guys who discovered it. And when moonshine came along, Conway just coined this name monstrous moonshine because it sounded really cool. You know, you've got moonshine sounds indicates that the connection between the monster group and the elliptic modular function is completely crazy, and moonshine is alliterative with monster. So they wrote this paper on monstrous moonshine, and ever since then the name monster got stuck. And it's, you know, so it's either called the monster or the Fisher-Grice monster.
All right, another question we got was, I believe for the number like e to the pi times square root of 163, but like what does it have to be doing to an integer? Like he says he understands that it's like related to the functions by Kleene.
Okay, this gets into some fairly deep mathematics called class field theory and complex multiplication. The simple version is that e to the pi times the square root of anything is always something called an algebraic integer, which means it satisfies a polynomial with integer coefficients, a leading coefficient 1. And occasionally, this algebraic integer happens to be an honest integer. And there are only a finite number of cases when this happens. And figuring out this finite number of cases is actually a very difficult problem, which was solved only finally solved a few decades ago. Square root of 163 is in fact the largest number for which e to the pi times the square root of something is an exact integer. So, sorry, is very close to an integer. So I'd say if you want to find out more about that, you would Google complex multiplication on Wikipedia and chase down the references there.
Somebody was wondering what applications of this field of mathematics have already been discovered.
Applications. Which field? Are you talking about group theory or moonshine or sporadic groups?
I think he means the sporadic groups. Yeah.
Sporadic groups, there are almost no applications outside pure mathematics that I know of. There's one very minor one. If you take the sporadic group M24, it's closely related to something called the Golay code. And the Golay code allows you to transmit information very efficiently. It's able to correct errors. And this has been used in one or two space probes. But apart from that, which wasn't really necessary. I suspect they didn't really need it for the space probe. They were just using it for the space probe because someone thought the M24 was really cool and thought it'd be fun to use it for the space probe. So I think the honest answer is sporadic groups don't really have any use outside pure math.
All right. Another question we got was what is it like being a mathematician? And like how rare is it to make a breakthrough in math? And who would you advise being a mathematician?
Well, it's very hard to answer this because, as everybody knows, AI has very recently started being almost as good as professional mathematicians. So what's it like being a mathematician? What it used to be like is, I think the analogy is as follows. There's a large concrete wall and you're trying to break it down, and you do this by hitting it with your head repeatedly until you find a weak spot. And most of the time you don't find a weak spot, you just get a bad headache, and you just have to keep going until maybe you find a weak spot and maybe you don't. So mathematics research is like that. You sort of spend nearly all your time trying very hard to do something that just doesn't work. AI is getting to the point where it can try out all these hard things very much faster than humans. So it's not yet as good as professional mathematicians for most problems. So most of the things it solved are finding unexpected counterexamples. But in 5 years, I think being a mathematician may have changed radically.
Somebody was wondering what inspired you to do math? Like, how did you know math was the thing for you?
Wasn't much good at anything else. I think it's like asking, how I never really seriously considered anything else. It's like asking a tree why did it decide to be a tree rather than something else. Well, it just was a tree. I just was a mathematician. I was just very interested in mathematics, and not all that much interest in all the other things they tried to waste my time on in school.
Uh, this is a question I from myself. I was wondering, like if you ever take breaks in between your math sessions, what's like a activity that helps you refresh your mind?
Taking breaks from math sessions.
Like, is there any specific thing that helps you like think better or like, because when I do math, a lot of times I get burnt out and yeah.
Yeah, I don't know. I don't really ever stop doing math for long periods of time. Um, what you can do is you can take a break by working in a different area of mathematics. I don't know if that really counts. So what I can do is if I get bored of working on some problem, I can just do background reading in some completely unrelated area of mathematics. Or you can do the things everybody does for taking breaks. You can go for walks or watch movies or something. Um, um, I mean, John Conway had this suggestion that you should actually work on several different problems at once. So you have a really hard problem you're working on, which is the one you really want to solve. But if you want to take a break from it, you have some background routine calculational problems that you know you can make steady progress on.
Okay, someone else wanted to know, what do you wish that younger you had known before the position you're in now?
What do I wish I'd known when I was younger? That's an easy one. I wish I'd known to buy Bitcoin in 2010.
Okay, great. Wait, there's also one more question. What is your advice for people seeking to enter mathematics, hoping to make an unlikely discovery?
I would say if you want to make an unexpected discovery, you need to know a little bit about everything. So, for example, if you look at John Mackay's absolutely bizarre discovery, he happened to be looking at sporadic groups and he happened to be looking at elliptic modular functions. And these were two areas that everybody thought had absolutely nothing to do with each other, that they were totally unrelated mathematical areas. So if you know little bits about huge numbers of different mathematical areas, I mean, you don't have to be experts in all these areas, you just have to have a sort of rough overview. This greatly increases your chance of noticing some really unexpected discovery. That was the rule before AI became good, of course. I mean, in a few years, AI is going to be able to do this, discovering unexpected relations much better than any human. So I don't know what humans are going to have to do to make discoveries in the next few years.
Okay, I think that's it for the questions. So thank you everyone for coming, and thank you, Professor Borcherds, for giving the talk.
Yeah, thank you. This was really interesting. Yeah.
Okay, well, goodbye to everyone then.
Yeah, thank you so much for giving this talk. We really appreciate it. Yeah.